Section 4.6 is going to give us the missing piece of the puzzle that we need to be able to do everything that I want you to do with polynomial functions. So we're going to be looking at complex zeros in the fundamental theorem of algebra. Anytime you see the word fundamental in something, it's probably pretty important. Are y'all familiar with the complex number system? That's the one with the I, where I is the imaginary unit and it's equal to the square root of -1. The complex number system encompasses all of the real numbers. Complex numbers are written in the form a plus bi, where a we call the real part of the number, b is the imaginary part. So if we have a real number, I can write the real number 0 like this, or I can write the imaginary number 0 like this. A variable in the complex number system is referred to as a complex variable, so this would be a complex variable if it's written in this form. A complex polynomial function f of degree n looks just like our polynomial functions of degree n, only now these coefficients are going to be complex numbers and the leading coefficient cannot be 0. And n, once again, is a non-negative integer, so these powers on the variable x have to be positive integers. A complex number r is a complex 0 if the polynomial is equal to 0. Anywhere the value of a polynomial function is equal to 0 is called a 0. So what we've been looking at up to this point were real zeros. Now we're going to look at complex zeros. Well, that creates a problem when graphing, because when we're graphing, what we're graphing is on the real number line. When we look at this is our x-axis and y-axis, and these are on the real number lines. Well, what do these complex zeros do? When you have something that turns like this, your complex zeros are going to be this turning point up here. So now let's look at the fundamental theorem of algebra. Once again, fundamental means it's important. Every complex polynomial function of degree 1 or larger has at least one complex 0. Every complex polynomial function of degree n equals 1 can be factored into n linear factors, not necessarily distinct in this form, where real numbers and complex numbers are also going to be complex numbers. That is, every complex polynomial function has exactly n complex zeros, some of which may repeat. Now, this is different from our regular polynomial function. When these are real numbers, we're not guaranteed that we're going to have the same number of roots as we do the power here. In the complex numbers, we do. Okay, so if it's a 5th degree complex polynomial function, then we're going to have 5 linear roots. And our complex roots are going to come in what's called conjugate pairs. The conjugate pair of a plus bi is going to be a minus bi. What happens if we multiply a plus bi times a minus bi? This is the difference of two squares. So that ends up being a squared minus bi squared. Well, this is a product, and we can distribute a power across a product, so that's going to give us a squared minus b squared times I squared. But what is I? Square root of -1. So when we square I, we get -1. So this ends up being a squared plus b squared. Well, wait a minute, that's a perfect square sums, which we said couldn't factor. In the real number system, it can't factor. In the complex number system, it has linear factors that are conjugate pairs. Isn't that cool? The fundamental theorem of algebra says every polynomial function can be factored into a product of linear factors. Whenever you have a conjugate pair, it results in the real number system, a quadratic factor. That means that every polynomial function in the real number system can be factored into a product of linear or quadratic factors. You see, these are all linear factors. That's a big deal because they're all powers of 1. But these are complex numbers, and I just showed you that complex numbers come in conjugate pairs. So if you FOIL out a conjugate pair of complex numbers, you end up with a quadratic real number. So since this happens for the complex numbers, that means every real polynomial function will either be a quadratic or a linear factor. When you take advanced algebra, that's when it starts gelling for you. But I'm telling you now because some of you may decide to be math majors and take abstract algebra. So let's look at how we can use the conjugate pair theorem to figure some stuff out. It says a polynomial of degree 5 whose coefficients are real numbers has zeros -2, -3i, and 2 plus 4i. Find the remaining two zeros. A polynomial of degree 5, that means the power function for it is going to be f of x equals x to the 5th. So we have to be able to write out, according to the fundamental theorem of algebra, 5 of these products here, right? 1, 2, 3, 4, 5. And we could be off by a constant. It could be positive or negative. So we end up with f of x equals a times all of this stuff. A could be a constant. It gives us a family of functions. This first factor, if -2 is a root, what does the factor have to be? Plus 2. If -3i is a root, what does this have to be? Plus 3i. But what do we know about this root? There's also another one, minus 3i, because this conjugate pair theorem said that any imaginary roots come in conjugate pairs. So that means that this one will be x minus 2 plus 4i, and then this will be x plus 2 plus 4i. This has to be a solution, and this also has to be a solution. I get my solutions by setting each factor equal to 0. So if I set x plus 2 equal to 0 and solve for x, I get x equals -2. If I set x plus 3i equal to 0 and solve for x, I get x equals -3i. And that would give us the conjugate. So that's x equals positive 3i. Here, when I set this equal to 0, I get x equals 2 plus 4i, but here, okay, so it does have to be a negative. X minus 2i equals 0, and then we end up with x equals 2 minus 4i, and that is the conjugate pair. Okay, 3i can be written as a complex number by writing 0 minus 3i, and then the conjugate pair would be 0 plus 3i. Well, that's this right here. 2 is the real part of this answer on the conjugate pair. Let me roll back up. This deserves clarifying. We know that if 2 plus 4i is an answer, 2 minus 4i has to also be an answer. And you're struggling with where my brain was balking, because you only saw the imaginary part that I wrote down. Had I have only written down the imaginary part here, this would have been x minus 4i, and when you distribute the negative, it works that way. Here, this would give you x plus 4i, because a negative times a negative, but in your answer, you got the minus 4i. You're only looking at the imaginary part of the complex number here. Here, you're looking at the real and the imaginary. Okay, my next step to you was to write the real polynomial. So that means I want you to get rid of the imaginary numbers here. So how we're going to do that is we're going to multiply the conjugate pairs together. So our function now is going to be f of x equals a times x plus 2 is a linear factor. When I FOIL out x plus 3i times x minus 3i, I get x squared plus 9 times, and I'm back to needing to do scratch work again. It's not just a straightforward FOIL is the problem. It's multiplying a trinomial times a trinomial, because what I have right now is x minus 2 minus 4i times x minus 2 plus 4i. When I distribute the negatives to these factors, that's what I end up with. I'm going to multiply using distribution. So that's negative times positive is a negative 16i squared. This is going to give us a minus 8i and then 4xi. Are y'all seeing what I'm doing here? I'm distributing this to these three terms. Now I'm going to do the same thing with the negative 2. That's going to give us a negative times negative is a positive 8i and a positive 4 and a minus 2x. I'm just lining up like terms. And then next I'm going to come along and I'm going to distribute the x's to these three terms, and I end up with minus 4xi plus 2x and an x squared. And when I add up my like terms, these are going to zero out, these are going to zero out, these are going to zero out, and I get x squared plus 4 plus 16. Because I squared is negative 1 and negative 1 times negative 16 is positive 16. So all of this is scratch work, which means that our real fifth degree polynomial is going to be f of x equals a times x plus 2 times x squared plus 9 times times x squared plus 20. This is our real 5th degree polynomial. Yes, sir. I should have. Yeah, this should have been a negative. That's going to change this to an x squared minus 4x. This is going to be x squared minus 4x plus 20. So that then would be our final answer. There's no factoring to be done here because that's a quadratic that won't factor, and this is a quadratic that won't factor in the real number system. Multiply it out. No, because see, what we're going for ultimately in calculus is I want to know, can you take this function and factor it? That was so much fun. Let's do it again. Find a polynomial f of degree 4 whose coefficients are real numbers that has the 0. And here we go. So it looks like x minus 1 is going to be a repeated root. So we have f of x equals a times x minus 1. It's a repeated root, so it's going to be squared. And then this is going to be x minus 4 plus I times x minus 4 minus I. If I asked you to find a real polynomial, which is what I'm intending you to do here, we would need to do what to these numbers? FOIL it out. Let's get the quadratic that this comes from. So when I FOIL this out, I'm going to have, if you want to do it sideways, you can. We're going to multiply or distribute the x. And that's going to give us x squared minus 4x plus xi. And then we're going to distribute the negative 4 to each of these terms. And that's going to give us minus 4x plus 16 minus 4i. And then we can distribute the I to each of these three terms, and that's going to give us minus xi plus 4i minus I squared. Now we've got like terms to combine. So this is going to end up being x squared minus 4x is minus 8x plus xi minus xi cancel, minus 4i plus 4i cancel, and we have 16 plus 1 is 17. So my real polynomial is going to be f of x equals a times x minus 1 squared times x squared minus 8x plus 17. How many turning points are there going to be here? At most 3. If the degree is 4, the maximum turning points is going to be the degree minus 1. It's multiplicity, so it's going to touch and go at the x-axis. Only one of these. So right here at x equals 1, when we draw the graph, it's going to touch and go. Is this going to open up or down? Well, it depends on the sign of a. It's going to touch and go, and then it'll touch and go again, but the endpoints are going in the same direction. If a were negative, the graph would look something like this. Rational zero theorem. Let f be a polynomial function of degree 1 or higher of the form, there's our polynomial function where each coefficient is an integer. If p over q in lowest terms is a rational zero of f, then p must be a factor of this number, and q must be a factor of this number. If you have any rational number that's going to be a solution or a root here, it's going to be factors of the constant term, that's the p, divided by the leading coefficient, that's the a sub n. On this problem, if we're asked to list the potential rational zeros of this polynomial, we're listing all of the factors of 12. 1, 2, 3, 4, 6, and 12. Q is going to be all factors of the leading coefficient, and 3. If we like prime numbers, there's fewer choices. So I take each of these factors here, and I divide by each of these factors here, and those are all the possible rational roots. There could always be irrational roots. When I list all possible rational zeros, well, that's going to be 12 divided by 1, 12 divided by 3, 6 divided by 1, 6 divided by 3, 4 divided by 1, I've already got it, 4 divided by 3, 3 divided by 1, 3 divided by 3, 2 divided by 1, I've already got that, and 2 divided by 3, could be positive or negative. 1 divided by 1 and 1 divided by 3. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible choices for rational roots. And you're sitting there going, Why do I want to know this? Well, because if I ask you to factor this, because there's an odd number of roots, it's possible to have 3 real roots or 1 real root. Because if there's an imaginary root, it comes in conjugate pairs. So it eats away 2 at a time. Let's look at this. It wasn't asked, but I'm carrying you beyond because we have this information and we can put it together. So there's a possibility of 3 real roots and no complex, or we could have 1 real root and 2 complex. Is it possible to have 3 complex roots? No, because they come in pairs, which means even numbers. That's why when you have an odd power on your polynomial, it's going to cross the x-axis at least 1, because there has to be 1 real root. And the rational roots will be one of these numbers, so you've narrowed down your choices on what those rational roots can be. Okay, if the power is 3, the most number of x-intercepts or real roots you can have is 3. If you have 3 x-intercepts, there's no complex. The fundamental theorem of algebra says that the most number of linear factors you can have from the complex system is going to be equal to the power. So if I have a polynomial of degree 3, then I could have no complex roots and have 3 real. Or I could have 1 real root and then a conjugate pair, which would be 2 complex roots. Can you have 1 complex? No, because they come in pairs. They come in 2s. A plus bi, a minus bi. So you can't have an odd number of complex roots. Let's look at a problem here how we can use this. It says find the complex zeros of the polynomial function and write f in factored form. If I'm going to factor this, if I have any real roots, first of all, it's possible that we could have 4 real and no complex. Or I could have 2 real and 2 complex, no real, and all 4 could be complex. One way to check right fast what types of roots we have is to go ahead and graph this. When we graph this, if it does not cross the x-axis anywhere, what does that tell us? That we have 4 complex roots. If we cross the x-axis, we're going to cross at least twice. Let's go ahead and write down our possible real factors. What are the factors of p? What is p? 20. So the possible factors are going to be 1, 2, 4, 5, 10, and 20. And then q is 1. So we're going to go to the graph, and we're going to put in our function. Ooh, we've got stat plots on. We're going to turn those off. And we're going to graph this function on my window. Because I know negative 20 and 20 are possible rational roots, I want to at least let my x's go from negative 20 to 20. So I'm going to go from negative 25, just so that I'm sure to grab them, to 25. And I'll let my x scale be 5. Because I don't know what the y's are going to be, I'm going to do a zoom fit. That's zoom 6. And it looks like I'm going to have 2 x-intercepts. And these are at multiples of 5, so it's looking like it might be at 10 and negative 10, but I need to make sure. Do you see what I just did? I don't have the whole graph in this picture because it should have gone out further. But I have enough that I can see that I'm going to have x-intercepts at 10 and negative 10. But I need to make sure. Try plus or minus 2 for our real zeros. We'll start with 2. So we have 1, 2, 1. Sir? We're going to do that next. What we're doing is we're going to work this 4th degree polynomial down to a quadratic that we can then use the quadratic formula to solve. When I check the 2 right here, what I'm doing is I'm dividing this by x minus 2. I changed the sign of the factor. So this means that x minus 2 is going to be a factor if this works. So I'm going to multiply with blue, and I'm going to add with green. We begin, though, by dropping down the 1. It just comes straight down. And then 2 times 1 is 2. 2 plus 2 is 4. 4 times 2 is 8. 8 we add and we get 9. 2 times 9 is 18. Minus 8 is 10. And 2 times 10 is 20. And we get 0 here. Anytime you get 0, that means that you've factored this. It goes in evenly. There's no remainder. So what we have right now for our factors is going to be x minus 2 times x to the, we started out with a 4th. This is now x to the 3rd plus 4x squared minus 9x plus 10. That's what this means right now. I've taken a 4th degree polynomial and factored out a linear factor, and now I've got a cubic. So what we're going to do now is we're going to take these numbers and we're going to divide this by x plus 2, or a negative 2 on the outside. First step, drop down the 1. It stays a 1. Negative 2 times 1 is negative 2. Negative 2 plus 4 is 2. Negative 2 times negative 2 is, negative 4. I think I said it wrong, but I wrote it right. 9 minus 4 is, and 5 times negative 2 is, and when we add this together, we get 0. So that's going to give us a 0 here. So now we have this polynomial factored into x plus 2 times x minus 2 times x squared plus 2x plus 5. I divided by x minus 2. I factored it out. What's left is, these are the coefficients for the cubic. So this goes x to the 3rd, 2nd, 1st, constant. And then when I divide off another linear factor, x plus 2, the x minus 2 is still there. And now these coefficients become the coefficients of my quadratic factor. So now we have our 2 real factors. We have to come up with our 2 complex factors. How do we get the 2 complex factors? We use, alright, so what is A going to be in this problem? 1, what is B? What is C? So now we're going to just plug and chug, plug in the numbers. So we get x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2 times 1. This simplifies into negative 2 plus or minus the square root of 4 minus 20 all over 2. So we get negative 2 plus or minus 4i, because this is negative 16. The square root of negative 16 is 4i, all over 2. So that's going to simplify into negative 1 plus or minus 2i. When we look at our zeros now, we're looking at f of x equals x plus 2 times x minus 2 times x minus negative 1 plus 2i, and x minus negative 1 minus 2i. So we don't want to leave all these parentheses here, so what we would do is rewrite this as f of x equals, distribute the negative, and there is the completely factored with real and imaginary factors. If I only wanted the real factors, I would have stopped right there. Oh, this is the quadratic formula right here. You're supposed to have that memorized in high school. What I would do is, at this point, I would distribute the denominator. I didn't show that step. Okay, what I would do is I would rewrite this. I would show this step where I did negative 2 over 2, do the real part over the denominator, plus or minus 4i over the denominator, and then try to reduce. When you have fractions, if you have a over b plus c over b, you can write it spread out, or you can write it shoved together. This is shoved together, this is spread out.